We move on to construction of elementary flows in 2D. So far we've looked at the Laplacian and how we can find the fundamental solutions of it. But more importantly, without even going into the boundary conditions, a wealth of solutions have been obtained in which the solution is obtained first and then it is seen that which boundary condition the solution is most applicable to. So let us look at the first such construction, that is of a dipole. So a dipole is something which comprises of a source and a sink. So if this is the source, then mass comes in like this, and if this is a sink, so this one is the sink, so mass comes in like this. If this is the source, then mass goes out like this, and because of the proximity you can expect mass to come out from this source and enter into this sink. So it will lead, we expect that it will lead to a pattern like this. Let us see mathematically how we can construct this. The fact of the matter is the equations are linear. In fact, the equations are linear, and if there is a point mass source, then this becomes plus m upon 2 pi. Well, this one is not m upon 2 pi, this is simply m times the delta function at the particular point. So x vector minus x prime vector. So this is the delta function that we've discussed in the previous lecture, and if there is a point vortex, then we have a minus delta x minus x. So we've already seen the fundamental solutions of these, and we can use this to construct this kind of a solution. So let us consider a source of strength plus m at minus epsilon comma 0 and a sink of strength minus m at epsilon comma 0. So I'm not going to go over the solution for this once again. I'm simply going to write down the solution. So the solution for the velocity potential is m upon 2 pi ln square root of x plus epsilon whole square plus y square plus minus m upon 2 pi ln square root of x minus epsilon whole square plus y square. So this comprises the solution. So this is called as the velocity potential for a doublet. So let us look at how this doublet will look like in the limit as epsilon tends to 0 and the strength goes to infinite. So this distance is essentially 2 epsilon. So if this is the origin, this one is epsilon and this one is minus epsilon. So the dipole vector is the summation of the location times the strength, and in this case it will be minus epsilon ex vector times m plus epsilon ex vector times minus m. So this one is the contribution from the sink and this one is the contribution from the source, and this comes out to be minus 2m epsilon ex. So this one is the definition of the dipole vector. So now with this definition we can go ahead and simplify this particular expression. The simplification is as follows. So the log of square root of x plus minus epsilon whole square plus y square can be written as log square root of x square plus y square plus minus twice epsilon x plus epsilon square. I've just expanded this particular term as a quadratic. So now x square plus y square is equal to r square. That is, if this is the origin, this the location r, the magnitude of this will be square root of x square plus y square. So this becomes log of square root of r square plus minus 2 epsilon x plus epsilon square. So if we take r square common, so this becomes log of r square root of 1 plus minus 2 epsilon x upon r square plus epsilon square upon r square. Now log of a times b is log a plus log b, so this becomes log r plus log 1 plus minus, so there will be a half over here, 1 plus minus 2 epsilon x upon r square plus epsilon square upon r square. So basically log of square root of any number is half log of that number. It's just basic logarithms. So this becomes ln r. So log of 1 plus x is 1 plus rather x plus x square by 2 plus x cube by 3. So basically we make use of this expansion. So this becomes half plus minus 2 epsilon x upon r square plus epsilon square upon r square by 2 and so on. So if we retain only the first term, this approximates to log of r plus minus epsilon x upon r square. So this is valid when the higher order terms are smaller than the leading order terms. That is, this term dominates over all the other terms. Do not be confused between this epsilon, is just to show the expansion of log of 1 plus x, nothing else. This is something which you might have studied in your class 11 or 12. So the approximation is this. With this approximation in mind, we can write down the velocity potential. So let me copy the expression from above. So this becomes m upon 2 pi ln r plus minus, rather this will be simply plus. We've done the general expansion of the expression above, so this will be plus epsilon x upon r square, and this will be minus m upon 2 pi ln r minus epsilon x upon r square. So these two terms cancel out, and we are left with simply m upon 2 pi epsilon x upon r square times 2, because this minus combines with this minus to become a plus, and this is what we obtain. So this 2 cancels out. So this is simply m epsilon upon pi x upon r square. This is the expression for the velocity potential. And if we look at the definition of the dipole, so d vector was 2 epsilon m ex. So if this is true, we can write down the final expression as, okay, so I think we missed a negative sign. Yeah, so this is negative of this, so there is a negative sign over here. So using this, so what is the expression for m epsilon? M epsilon is, so let us multiply everything by 2 and divide by 2. So 2 epsilon m x, so this is what, 1 upon 2 pi r square. So this is nothing but minus d vector dot x vector. So look, minus d vector times x vector, if you do the math, x vector is xex plus y ey. So if you take the dot product of these two, we obtain minus 2 epsilon m x, and ex dot ex is 1, ex dot ey is 0. So this is what you obtain. So using this, we can write down this. So the velocity potential is in this particular form. Moreover, d dot ex, so x vector is also r cos theta ex plus r sin theta ey. And using this particular dot product can be written as 1 upon 2 pi r square. So this will be minus magnitude of d. So basically the dipole vector is in this direction, but the x vector is in, rather sorry, the dipole vector is in this direction, but the x vector is in this direction. So the cos of minus of, so the dipole vector is in the opposite direction of x. So this will be simply mod of this, mod of x vector times cos theta with the appropriate negative sign. So mod of x vector is nothing but r. So this becomes 1 upon 2 pi r. This becomes minus d times cos theta. Or essentially we can write it as minus d upon 2 pi cos theta upon r. Actually, we have already accounted for the minus sign over here. The fact that the dipole vector is in facing in this direction. So this is the direction of minus d. So the direction of d will be in this direction. You can work out the maths. It's a small oversight on my part. So yes, this will be the correct expression for the velocity potential. Okay. So you can easily plot this velocity potential, and the important thing is we've obtained an expression for a flow structure which looks something like this. We can now combine various fundamental solutions to find out higher order solutions. So suppose we want to find out the flow past a half body. So half body is something which looks something like this. So basically I want to find out the flow like this. So how to do that? So basically this resembles two things. It's a uniform flow like this plus a point source. So point source will be something like this. So now you can imagine when you combine these two, you have, let us say this is the point, this is the axis, this is the point where there is a mass source, and you have a uniform flow like this. So the outcoming flux from this point will interact with this uniform flow, and it will cause this uniform flow to deviate. So while it will have these kind of streamlines, there will be a point where the streamline will simply go like this. Okay, and there will be a stagnation streamline as well, that is the streamline where the velocity is 0. So that particular streamline will be the stagnation streamline. So what is the solution for this? So solution for phi would be uniform flow, which is this particular solution, plus a mass source. So m upon 2 pi ln of square root of x square plus y square. So this is a mass source at the origin, while this is a uniform flow. So the corresponding stream function, and you can easily find this out, and it should be obvious how to find this out. It will be uy plus m upon 2 pi tan inverse y by x. And the way to find out the stream function given velocity potential, or the way to find out the velocity potential given a stream function, we've already covered in the previous lecture. It simply implies mapping of velocity from one description to another. It's as simple as that. And remember, whenever you find these solutions, grad phi lines and grad psi lines must be orthogonal. Okay, so with this in mind, let us proceed to find out the components of velocity. So the velocity components can be simply find out. So the u vector will be simply the gradient of phi, that is u will be del phi del x and v will be del phi del y. So in this case u becomes capital U plus m upon 2 pi times x upon x square plus y square. I've simply taken a derivative of this expression with respect to x, and y will be equal to m upon 2 pi y upon x square plus y square. So these are the two expressions. When is there a stagnation point? From this particular diagram, it is clear that the stagnation point would be somewhere, I mean, it is very easy to see that the stagnation point would be somewhere on the x-axis itself. That is where this flow and this mass entry from this point will collide and make the velocity equal to 0. And remember, if this is a stagnation point, the entire streamline will be also a stagnation streamline. So let us check the velocity. So the velocity at, so we will substitute y equal to 0. So u becomes capital U plus m upon 2 pi 1 upon x, and v velocity becomes 0. Obviously the v velocity would be 0 at the x-axis. So this velocity, it would become equal to, so when is this velocity equal to 0? When is u equal to 0? So minus u is equal to m upon 2 pi 1 upon x stagnation. So x stagnation is equal to minus m upon 2 pi capital U. Well, something that I said was not entirely correct. We found out that this location, so if this is the origin, then at a distance equal to m upon 2 pi u, so this distance is m upon 2 pi u, you have the point where we have stagnation point. So this is a stagnation point. So this particular streamline is therefore a stagnation streamline. It does not mean that the velocity is zero everywhere on the streamline. It means that if we just focus on this particular streamline, let me rub it and draw it again. It means that if we focus on this particular streamline, there will be velocity along the streamline, but there will be no flux across a streamline, because we know that there is no flux across a streamline. So there will be a slip velocity because we are considering ideal flows, but the stagnation point, it lies at a distance of m upon 2 pi u on the left side of the origin. So this is the location of the stagnation point. Let us find out the value of the stream function So stream function at stagnation. So the stream function is given by uy plus m upon 2 pi tan inverse y by x. So we'll substitute y equal to 0. So if this is to be the stagnation point, then y will be equal to 0 and x will be equal to this. So y0 is this, m upon 2 pi tan inverse y by x. So y is 0 but x is negative. So it's approaching 0 from the other side. So this will be pi. So I'm giving it a minus because it's telling that it's approaching 0 from the other side. So this will be m upon 2. Yeah. So this is the value of the stagnation streamline. You can take your time and do all these calculations. Don't have to be hurried as me. Okay. So now that we know that this is the flow structure, this is the y-axis, this is the x-axis, this is the origin, and this is how the stagnation streamline would look like. The value of psi is equal to m upon 2. So now you can find out the span at any distance. So basically at a certain r you can find out what the exact coordinates will be. Okay, and it can be easily shown that h max, that is the maximum span of this, the maximum span of this. So the slope will tend to become constant after a long distance. So this span, which we call as h max, it can be shown that it is equal to m upon 2u. Okay, so basically how to find this out? So psi is basically u y plus m upon 2 pi. So this y by x is essentially theta. So if this angle is theta, tan inverse y by x will simply become theta. So as theta tends to 0, this particular term will vanish and the value of the stagnation streamline is equal to m upon 2. So this will be u h max. So this is how you obtain the expression for h max. So h max is equal to m upon 2u. So now what do we get from all this? So if we have a half body like this, right? So first of all, the stagnation streamline is a streamline across which there is no flow. So that is like a solid boundary. So it's like a solid boundary where there is no flow going in. So this entire situation can be considered to be a flow around of, of this half body. So this kind of object is called as a half body. The half body is determined by the stagnation streamline. There is no flow into the half body, and whatever flow originates inside the half body also remains trapped within the half body. Okay, so we can find out the pressure distribution on top of the half body. So using Bernoulli theorem, and the reason we can use Bernoulli theorem because the flow is irrotational everywhere, we can write down P plus half rho u square, the magnitude of the velocity square, is equal to constant. So what is the flow at infinity? That at far stream we can write P infinity plus half rho capital U square. That is, this is the Bernoulli term at far stream, and this will be equal to P plus half rho U square on the surface, and on the surface we imply on the half body, and by this we imply on the stagnation streamline. Okay, so we can define the coefficient of pressure, rather the pressure coefficient. It is also called as the Euler number because Euler did a lot of analysis of such kinds of ideal flows which are devoid of viscosity. So it is defined as P minus P infinity upon half rho capital U square. So this comes out to be, so P minus P infinity is nothing but half rho capital U square minus half rho mod U vector square upon half rho capital U square. And this is nothing but half, so 1 minus mod U square upon capital U square. Now the expression for this velocity, so U vector, we have already seen that it is equal to m upon 2 pi ln, not ln, this will be x upon x square plus y square, and this comma m upon 2 pi y upon x square plus y square. So this is how the velocity is. So now you can take mod u as square root of this square plus this square, and you can substitute this. Now the important thing is x and y are not randomly chosen. X and y are chosen so that they lie on the stagnation stream point, stagnation stream function. So how do you find the values on the stagnation stream function? So if you choose a certain x, you know that this stagnation stream function has this particular form. So once you have fixed x, then automatically y has to be found out using this. So m by, so let me just quickly write it down. Once you've chosen x, then how to find y? On Psi stagnation. So the Psi stagnation is nothing but uy plus m upon 2 pi tan inverse y upon x, but Psi stagnation is equal to m upon 2. So if you fix up the value of x, you will then have to solve the transcendental equation in order to ascertain what the value of y will be. In fact, it is easier to choose y and to find out the x. So how to do that? If you fix y, so m by 2 minus uy chosen times 2 pi upon m, tan of that is equal to y chosen upon x on the stagnation streamline. So the x that corresponds to the value of y chosen will be correspondingly this. So then you can substitute these values over here, find out the magnitude of the velocity, and find out the pressure distribution. So we're not going to go into the detailed specifics of it, but the pressure distribution over the half body. So if this is the half body, I'm just showing it in one axis. The pressure distribution will be higher over here and it will be lower on the other part. So there is positive pressure over here while there is a lift over here. So the interesting thing is, if you integrate this pressure over the entire surface, it comes out to be 0. So if you integrate pressure over the entire surface, so ds is this particular integration, it would come out to be 0. So we've looked at how to construct a half body. In what follows, we will look at how we can construct a flow past a cylinder.